Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Okay, step on inside, guys, and I don't do as many uploads here this year as you've noticed, at least in the beginning so far, because I've made other videos before that tailor to my students' needs, and ultimately, I won't say that's the overall goal of the channel. Well, it sort of is. You'll always see videos here and there, but I need to sprinkle some more in that maybe I haven't covered yet, or maybe we didn't cover as topics, or I was too busy for at the time. So this is going to be one of those. If you want to find other videos in this series that kind of follow along with what I'm talking about right now, you want to look for things. This is going to be about what's called the rational root theorem. I should have led off with that. And the rational root theorem has to do with polynomials and making sure you know how to factor, you know how to use division of polynomials, potentially synthetic division. That's what I'm going to be using here. I think there's no reason I'll be using long division here. And eventually we're going to talk about solving complex roots with them as well. It goes into some things involving quadratic equations and, sum and difference of two cubes and, things like that. A lot of different things come into play. So I'll try to link some that are relevant to what we're doing here. And you're going to see another video eventually on complex roots, also possibly using the rational root theorem, probably a few days from now as well. And I hope to bring that one up. But, just in the series here, if this is just brand spanking new for you in an upload and you're saying, what's it based off of? Based off some of the stuff down below if I can get it up for you. So, rational root theorem here, I'm going to jump into. You might want to have a calculator handy. I'm going to take mine out time to time. I'll show you different ways that we are going to be seeking rational roots and finding them. And I have, let me look first here. I have 13 practice problems for us to do, 12 regular problems, and 1 word problem. We'll talk about what this is, what we're doing with it before I get started. But let's go ahead and jump in. So in the first, in these problems here, you're going to be asked to find the rational zeros of each polynomial function, then write each function in factored form. Okay, first of all, let's talk about the whole factored form thing. I'd love to just be able to factor these things on my own, right? If you've seen any of the previous videos down below and things like that, you might know that in a cubic quadrinomial specifically, there are sometimes ways that we can do something called factoring by grouping, which is great. If you pair off common factors here, don't write this by the way, you pair off common factors here, GCF of x cubed minus x squared is x squared, you're left with x minus 1, and I can factor out a negative 2 here, and I have 5x plus 4, and we could generally factor things down, but suddenly these aren't identical factorizations. That's because, excuse me, this isn't a combination of a binomial times a binomial. There are other ways that we can factor some things down if we knew what one of the factors were, and then we could divide it out. If I told you, and I don't know the factors right now, I don't know. If I told you that x plus 4 was one of the factors here, what if I divided this thing by x plus 4, then I break it down into a quadratic, that maybe that can factor more, maybe it can't, but at least I got a factorization of it. This divided by x plus 4 is this trinomial, this quadratic trinomial right there, and then we can go on from there. That would be awesome. And we can do that if 4, or negative 4 I should say, was a rational zero of this polynomial function. It may or may not be, and here's the thing, it can potentially be one. There are potential ones that can be based on how these things break down. I don't think I'll get too deep into the how, and I'll just talk about the what we're going to do here. We are going to find the rational zeros of polynomial functions. Rational numbers, meaning numbers that can be expressed as a fraction of 2 integers. No irrational values, no imaginary values. They can be whole numbers or fractions and or a combination of both. And I think these ones in this section here are all rational things only, so we can then keep factoring and breaking it down more and more and get into factored form that's more than just a linear binomial times a quadratic trinomial. I think we're going to at least be able to get 3 binomials multiplied, like that or something like that. So hopefully we can do that with each of them. I haven't done them yet. And generally we'll have to do that when it's not factorable. I imagine most all of them are not. Otherwise we would probably use a different scenario. But anyway, I just want to get your setup right there. We'll talk about how to find those rational zeros. And it says, well, it just says find the rational zeros. What we're going to do is there is a possibility of many different rational zeros here. And we're going to find out which one works. Okay. The rational zeros, here's what you're going to do. I am going to be listing, I think I call these ones my p-values. I don't want to get this wrong. Here, hold on a second. Let me pause. I call one p and one q. Let me see how consistent I was with another thing I've done in the past. Give me 1 second. Okay, I'm glad I checked it out because I knew p existed. I just wanted to see which one here. I'm going to use p here to represent something regarding the number 8. Not even negative 8, but just the number 8 there. You'll see what I'm talking about in a second. And then some things q regarding this 1 right there. Okay, this one right there. And let's see. Okay, this one's a 2 right here. So what we're going to do is we are going to list all factors of 8, the positive and negative ones, right? P is not just 8 times 1, but also -8 times -1 and things like that. So all the different factors of P, positive and negative, to possibly lead to things here. And all factors of Q, which are just 1 and -1, 1 times 1 and -1 times -1. We're going to list all factors of P and Q. So factors of that value, factors. And the possible rational zeros, if you think about how factoring works, the possible rational zeros of this thing, zeros are solutions or roots of this thing, can come from any combination of P's over Q's. Again, I don't think I'm going to get too deep into the why right now. My students can ask or I can talk to them about it, but I want you to kind of know the idea here. So all the different possible factors of P here, there's positive or -8, positive or -4, positive or plus or minus 2, and plus or minus 1. All these numbers can combine with another number here to multiply and get 8 when it comes to these zeros. Q here is positive or -1 right here. Now, when you divide all these numbers by 1, then all the only possibilities here are just the ones on top, plus or minus 8, plus or minus 4, plus or minus 2, or plus or minus 1. Okay, so those are the possibilities. Those are 8 different possibilities of things here. Here's what we're going to test, and here's what it discovers. We are going to try and substitute. I'm trying to think of, actually, I might write them the other way. I haven't done this in a long time. I want to find another video and see which way I tend to write these. I'll pause it again and go back to you in a sec. Here's what I'm going to do. I'm going to try and plug in, and I'm going to start with small numbers like 1. I'm going to try and substitute 1 into here. F of 1, right? F of 1, and that's going to be 1 cubed minus 1 squared minus 10 times 1 minus 8. Now, if you do that right now, you'll see that you get 1 minus 1, which is 0, minus 10, which is -10, minus 8, which is -18. This value is -18. That is not a 0. That is literally, that is not the number 0. So 1 is not considered a 0, a rational 0 of this thing. I'm going to test other ones. I want to test them until I get a 0, because the goal is this. Let's say that 1 was a 0. That means that x minus 1 would be a factor, because in the zero product property, it states if you multiply this thing with anything and it equals 0, that means that x equals 1 is one of your solutions to this thing. 1 being a 0, not literally the number 0, but 1 being a solution for x that gets you 0 for y means that you can plug it into here and get 0 out, or in its factored form. And if 1 doesn't get you a 0, then x minus 1 can't exist as a factor, because I can't substitute 1 into this to get 0 out. I want to find those values there. And the rational root theorem states that if you have, I believe, rational coefficients right here, not I believe, that's true. If you have rational coefficients in your polynomial, then your polynomial's possible rational zeros that exist can only exist out of the set of the P's and Q's, P's being your factors of your constant term, Q's being your factors of your leading coefficient. Right there, the pluses and the minuses. Now, they have to have, excuse me, they don't have to have at least one, but if they have one, it has to exist within here. Now, we're going to try and find all the different ones, and I know I'm spending a long time talking about that, but of course it's going to speed things up as we go. So I'm going to keep testing these, and that's where I'm going to use the calculator sometimes, not just to calculate these numbers here, but I'm going to let it plug in numbers for me as we go down the line. Once we find one of our rational zeros, we don't need to find all of them at once. Once we find one of our rational zeros, what I'm going to do is I'm going to divide out its factor and be left with a quadratic here. And hopefully I can factor out that quadratic as I know how to factor quadratics. That's going to be my goal there. So, and you might need more room than what I have written here so far. So let's check this thing out. I tried f of 1. That did not work. It gave me -18. Let's try f of -1 right here. And listen, I don't know what it is. I don't know which of the rational zeros there are. So I'm trying f of -1. That'll be -1 quantity cubed. And I'm going to speed this part up a lot more, especially if I use a calculator. Minus the -1 quantity squared minus 10 times -1 minus 8 there, which is -1 minus +1, so -1. And then plus 10, this actually might work, plus 10 minus 8, which is -2 plus 10 is 8, minus 8 is 0. That does work. So -1 is one of your roots. It's one of your rational zeros of this thing. If -1, x equals -1 is one of the zeros, then x plus 1 is one of the factors, because when you substitute -1 into here in factored form, you get 0. So if x plus 1 is one of your factors, what I'm going to do is divide this by x plus 1. And I'm going to use synthetic division for that. So I'm going to take this, divide it by x plus 1. That brings me back to my root of -1. This is assuming you know what synthetic division is. If you don't know what it is, that's where you're going to go to the other video and check it out. One of the ones linked down below. So -1 is my root here. Me saying I'm dividing by x plus 1 doesn't mean anything. I need the -1 root for synthetic division. So I have a 1x cubed minus 1x squared minus 10x minus 8 right there. So let's go and synthetically divide this. We got 1 times -1. Again, if you don't know what I'm doing here, this is where you go back to something else or use polynomial long division and check that one out here. And then, so 0, remember, is the remainder right there. So you're left with here, this thing factors down to, right? We're talking about listing factors here. X plus 1 times x squared minus 2x minus 8. So that is a factorization of this guy right here, the original polynomial. It is not a complete factorization if this quadratic can factor down still, and it can. Two numbers that multiply to make -8 and add to make -2, are -4 and +2. So we can factor that down to x minus 4 times x plus 2. And that is the full factorization of this thing right here. This is the factorization of that. So what did I do? What could have I done? What does the rest tell me here? What I did was I found one of my zeros for this function, meaning a value that I could substitute into the function itself and get 0 out. Those intercepts there represent the things you also get in factored form for this thing. -1 is one of them. That happens to exist as one of the numbers in this list right here, which are divided by the factors of your constant term, by the factors of your leading coefficient, all positives and negatives. Right there. So 1 did not work, -1 did. Now 4 also happens to be one of the rational roots in here, and so does -2. That means if I kept testing here, if I substituted 4 into here, I'm also going to get 0. If I substitute -2, I also get 0. Those are the only three values that would get 0. This is a full factorization of this. They're all rational. And they don't always have to all be rational roots, but if one of them exists, we then divide it out to get what remains here, because maybe we can keep factoring down on our own from that, and if not, we keep using the rational root theorem to keep finding values for ourselves. But this was a simple quadratic to factor, and we did it, and we're good. So that's the factorization. We got it. We're going to be moving on. Now again, some added benefits to some of these is as long as this is a 1x cubed here, or the leading term's a 1, then factors dividing by 1 or -1 just keeps the signs as they are. So we're not really changing much there. But let's look at the second one. We're going to list factors of 60 here when we do our p's over q's. I don't know. Should I do plus or minus? Here, I'll do it in increasing order. This seemed a little backwards to me. Plus or minus 1, plus or minus 2. Like, you know, these are what they can divide by, right? 60 can divide by 1, 2, and 3. 4, it can divide by a lot of numbers. 5, 6, not 7, not 8, not 9. 10, 12, 15, oh gosh, 20, I might miss some, 30, and 60. If I missed any, 6 and 10 are in the middle, so there should be 5 on that side, 5 on that side. Okay, that works out. These are all the possible factors there. Now, that's a bunch of them. That is 24 different possible factors. This being a cubic, we only need to find one of them, right? We'll test things until they work. Now, there's some internal tests we can do, some where you can try it and say, yeah, that's not going to work. If you tried 1, it's 1 plus 2 minus 23 minus 60. I'm not going to bother working with that. Now, don't always think that too small won't always work here, but I assume we're going to have to pick a little large here because we got to cube a number, square multiply by 2. If you try 2 here, 2 cubed is 8. Plus another 8 minus then 46 minus 60. Again, I think you need to get a little bit bigger than that. So here's where I'm going to use the calculator to help me. And I'm going to mention one more thing about synthetic division after I do synthetic division on this problem here. But let's go back here. I'm going to create this equation in my own calculator here. I'm going to take this y equals here, and I'm going to do x cubed, x, I think the third power is there, x cubed plus 2x squared. And you can do this on a bunch of different calculators. You can even use an online calculator for it. But the bottom line is you need to find a number. You need to find one of these to be rational roots right here. So there's my equation. And I can now substitute. Where is it? I haven't done this in a long time. I can now ask for specific numbers, and I can substitute my own here in this table. So 2 didn't work to me, and I'm not going to try the negatives yet. I'll just try these first. 3, 4. If I get a 0, I'm going to stop. 5. Okay, there's a 0. There's a 0 with my root at 5. That means if I substitute 5 into this equation, check it out. Hold on. If I substitute 5 into this equation right here, I'd get 125 plus 50 minus 115 minus 60, which is 175 minus 175, which is 0. So f of 5 gives me a 0. That means 5 is one of my rational roots. I can now use that rational root, synthetic division on that rational root right there, this 5, to then create this cubic into a quadratic, and then maybe I can factor that quadratic from there. So I'm going to have 1, 2, negative 23, and negative 60, like that. And then, we go ahead and do this synthetic division. Times 5 there. Again, if you don't know what I'm doing here, I can't spend the time on this video on it there. So this factors into x squared plus 7x plus 12. Okay, so this guy factors into, well, hold on, there's the x minus 5. Keep in mind, x minus 5 is the factor, whereas 5 is the root itself. And here's x squared plus 7x plus 12. Two numbers that multiply to positive 12 and add to positive 7 are 3 and 4. So x minus 5 times x plus 3 times x plus 4. And that's the full factorization of that one. You can see these will be able to speed up more the more I especially get to use the calculator and test things with it. I'm going to list possible rational roots. In some cases, I might just avoid, I'm going to try and list them. And then I'm going to do synthetic division on it. Now, a couple things I want to mention. 5 was one of the factors here, and negative 3 and negative 4 were also factors. So when I skipped 3 and 4 to try 5 there, after 5 I would have tried 6 and 10 and 12 and 15 and 20 and 30 and 60. 5 is the only positive number that would have worked here. And let's say 5 didn't work. I would have tried all positives. None of them would have worked, and then I would have had to do negatives. It's up to you however you want to test them. But I skipped past negative 3 and negative 4 in hopes that a positive worked, and it did. But if I tested negative 3, I would have gotten 0. Let me show you that. If I tested negative 3, I would have gotten 0. Whoops, not answer. Negative 3. And if I test negative 4, I would have gotten 0. And those are the only 3 zeros of this thing. They're all rational, and they all work there. That's one thing I want to mention. Second thing is, there's more than one way to test a 0 on this. I'm plugging values in, whether calculator or by hand. I'm plugging values in to see if I get a 0. You know how else you can do it, which I don't really recommend, is keep doing synthetic division each time until the first root that you test has a 0 remainder. So you can either plug the values in. I mean, listen, if the numbers get too big, maybe plugging the values in is a little too much. Me using a calculator helps. But if you keep using synthetic division until you get a 0 remainder, all's well. Only 5, negative 3, and negative 4 would have given me a 0 remainder. Any other number 1 would have given me some non-zero remainder. Remember, if we factor this thing down, that means there should be no remainder left. It should just be a product, no plus a sum. And we should be able to set this equal to 0, plug in these numbers, and make it work. So only those 3 numbers would have worked, and I can keep testing with synthetic division. I don't plan on doing that. I only plan on using synthetic division to divide after I find my root, and I'm probably going to use the calculator for the most part to do the root, but sometimes you can't use that the same way. Maybe you don't know how to do it on your own. So there are some little by hand things every so often. I don't know if it shows up here that you can kind of do and check things out. Always start smaller numbers first if you think it's easier for you to just plug and play. Okay, I'm going to move forward down to number 3 here and do the same thing. The difference is now there are more possible roots for our q's, right? Q's are factors of the leading coefficient. P's are factors of your constant. So my p over q possibilities here, I need to list my factors of p plus or minus 1, 2, 3, and 6. And then you can divide these by also possibly plus or minus 1 or plus or minus 2. Now again, dividing by 1 means all these are possible whole numbers here. So all the possibilities, there's positive or negative 1, 2, 3, and 6. But what if you divided these numbers by 2? What are also possible things? What is 1 divided by 2? Well, 1/2. So plus or minus 1/2 is a possibility. What is 2 divided by 2? Well, that's 1. We already have that 1 there. And what's 3 divided by 2? 3/2. Plus or minus 3/2 is possible. And I'm secretly hoping 1/2 or 3/2 is a possibility here, or at some point we get some fraction versions. I'm not going to test those first. I can plug it in the calculator should be fine, and that should be fast. But I'll show you why these are the possible things once I get more of a breakdown of the ones you see here and why fractions exist as possible ones if my thing factors in such a way. I assume one of these is going to be a fraction somewhere. You'll see why. Okay, so let's test some things. I'm going to substitute this back into my calculator one more time. Well, here, I'll test some easy ones. I'll plug it into the calculator. I think I'm going to use the calculator as often as I can. Problem is I got to type the equations back in. So going back to the calculator here, I got to type, and I got to click type, not type. So 2x cubed minus x squared minus 13x. I mean, you guys can probably hand do it. I can probably use my, if you trust what I'm doing on this calculator here, I can probably use my personal calculator and type those things in and say, this is what I found. You can try and plug it in. This is what I found. So I'm going to clear out my other values that I had, unless, oh, look, 3's a 0. Ha, I found one. So maybe I didn't have to clear out my values. All right, there we go. All right, well, 3's a 0. Awesome. Now listen, if I tested 1, 2, okay, none of those didn't work. 3 apparently works, and 3 is one of them, right? It's among my possible rational roots. So 3 is a 0, f of 3 equals 0. Awesome. So let's use synthetic division on 3 as the root, and we have a 2, -1, -13, and -6. Remember, you still have to divide. We know we'll get a remainder of 0 if all goes correctly, but we still have to divide to get this quadratic that comes up after this. So 15 and 2 and then 6 and 0 there. 0 remainder, that worked out. So this thing factors to, remember 3 is the root, x minus 3 is the factor, times 2x squared plus 5x plus 2. Not much room here. Now we're hoping this is factorable, and I can say that it is here. That thing factors down to, as I look at it, 2x plus 1 times x plus 2. 2 times 2 is 4, 1 times 1 is 1, 4 plus 1 is 5, and those are factors there. So this is the breakdown of that here. Now, what are the rational roots of these ones? We know that 3 was one of them, and -2 is one here. Is -1 one of them? No, it's -1/2, because if you consider this is 2x plus 1 equals 0, subtract 1, divide by 2, -1/2. That's your other factor, that's your other root, right? You see where you see where the roots come from. The roots come from what you're able to factor based on combinations of this first term and this last term. If you were factoring a quadratic, even such as this one right here, I know that this has to come from 2 times 1, and I guess this 2 times 1 as well, but those are the only factors of 2. You work possible factors of 2 until the right combination gives you this, and there are possible combinations with these that have a 2 somewhere, and some other numbers that multiply to 6 to make this thing work, and that's where it shows up here. And why does it have a fraction here? Because the 0 is when you set this to 0, subtract 1, and divide by 2. -1/2 is the value I substitute in here to get 0 out, because this x is multiplied by 2. So somewhere dividing by 2, taking half of it needs to happen, and that's where it is there. But that's the factorization. And that's why the rational root theorem comes from those possible things. Based on when you factor, that's the ones they possibly come from. Which one is it? Your guess is as good as mine. You got to test them. You got to test them and figure them out. All right, I got to move this thing on forward, and hopefully explanation made more sense, and I can probably run more through process. And I think with this next one, I'm going to use my actual calculator, speed up time a little bit, until I maybe find one that just works so easily that I can just try and plug in 1 and you're good. Remember, when you plug in 1, it's just, 1 minus 9 plus 23 minus 15. I don't have to think about what I'm computing. Give me 1 sec. Let me see if I have the calculator. I got to find my calculator. Give me 1 sec here. Okay, I'm back, and you know what? I should also show this kind of calculator here. I really wish I had a TI-30 as well, but when it comes to using these ones right here, there's a table button that I can use right there to then punch in an equation. I can hit edit function, and for example, I have like an x squared right there. You can edit functions there, and then you can ask for different things. You can either type f of something or go to a table just like I did in the previous one. So I'll give this one a shot right now. Again, I should keep moseying on forward. It's already 25 minutes in. I've done 3 problems. So, 3 of 13, and the last one's a word problem. So let's keep going forward, guys. Okay, number 4 here. We have g of x equals blah, blah, blah. So when it comes to factors here, your p's over q's, I'm going to try and write these out. It's over plus or minus 1. So you got plus or minus 1, 3, 5, or 15. These being factors of the number 15 right here. And these are the ones to test, right? Now, if I substituted 1 into here, something tells me that actually 1 might work. Last time I mentioned, so 1 minus 9 is -8. plus 23 is 15, minus 15 is 0. So 1 actually works. I don't even need the calculator for that. That's why I say just try 1 in your head, and it'll be obvious when it doesn't work in some cases. Some cases you're going to try it. So f of 1 equals 0 is the thing, therefore x minus 1 is a factor. Let's deep dive into that here. Let's do a synthetic division look at that with 1. 1, negative 9, 23, and negative 15 as we divide those guys out. 1 times 1 is 1, and then we get that negative 8, and negative 8 here, and 15, and then 15 and 0. And, I'm not sure if it occurred to me or not. Maybe it's just because it's that 1 here, but I did say 1 minus 9 is negative 8, plus 23 is 15, and all that kind of stuff. That probably is true, how those numbers come into play. It never occurred to me. But anyway, so this thing here then factors to x minus 1 times x squared minus 8x plus 15. And of course, this right here can factor down into x minus 3 times x minus 5. So apparently, 3 and 5 were also possible rational roots there. So that's the factorization of that guy. All right, let's change colors a little bit. Let's keep moving on down. So my p's over q's that I'm going to test this time are all factors of 8 over 1. So plus or minus 1, 2, 4, and 8. Let's try 1 to be savvy with this. 1 minus 5 plus 2 plus 8, that doesn't work. Let's try some. Well, let's try 2. 8, 2 cubed is 8, minus 20 is negative 12, plus, yeah, I think this works. Negative 12 plus 4 is negative 8 plus 8 is 0. So I believe 2 works. F of 2 equals 0. You can try it however you want, right? Use a calculator. Don't use a calculator. Whatever's fastest. Do what's fastest. You got some work to do on these. Synthetically divide here with 2. We got 1, negative 5, 2, and 8 right there. And 1, 2, negative 3, negative 6, negative 4, negative 8, and 0. So this factors into x minus 2, with 2 being the root, and times x squared minus 3x minus 4. So that guy becomes x minus 4 times x plus 1. 1 factor down. I don't think I'm going to save time and not really talk about that too much. Yeah, so it goes on, guys. I think, look, I'm kind of tired. I want to do as much as I can here. Okay, so this is one that's kind of interesting because this time your q is larger than your p here, which means there's probably more fractions that are possible. I hope there's at least one whole number, but maybe there's not, right? 6x doesn't have to come from 6 and 1. It can come from 3 and 2, which means you would have only fractions in that case. But listen, I'm going to use my calculator to test things. There's no way that I'm going to try 2/3 on this thing here. It's common denominator. See, I'm not going to do that. I'm going to use a calculator to work those ones out. And you can use a calculator to punch those numbers in, but I'm going to use the equation and enter them into a table. Anyway, my p's over q's here are plus or minus 1 and plus or minus 2 all over plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Factors of 6 there on bottom, factors of 2 on top. So what does that leave us with? All these over 1, so plus or minus 1, plus or minus 2. All these over 2, plus or minus 1/2, and 2 over 2 is 1. We already have that. And then plus or minus 1/3, plus or minus 2/3, and plus or minus 1/6, and plus or minus 2/6, which is 1/3. So we already have that one as well. So these are the possible combinations here. You know that I'm going to be searching for the ones with whole numbers first before I try some things in the calculator. 6 minus 7 minus 9 minus 2 is not going to work. Let's try negative 1. I haven't done much with negatives with you guys. That would be negative 6 minus 7, because negative 1 squared is positive. So minus 7 plus 9 minus 2. That is negative 13. That one doesn't work either. Let's try 2's before I do the whole numbers, fractions and equations. 2 cubed is 8 times 6 is 48. Minus 7 times 4, so that's 28. So 20 minus 18 minus 2. That one works. That one works here. So f of 2 equals 0. So therefore 2 is a root here. X minus 2 is a factor. Let's synthetically divide there. We have a 6, a negative 7, a negative 9, and a negative 2. Okay. So okay, so there we go. So this factors into x minus 2 times 6x squared plus 5x plus 1. Okay, hopefully, and I can probably assure you that this is factorable as well. It's either a 3x and 2x or a 6x and 1x. I'm guessing 3x and 2x because of the 5 being smaller than a 6. So this should factor into 3x, 2x. And listen, there's only one factor of 1, and that's 1 and 1. So plus 1 plus 1. That's 3x plus 2x, which is 5x. That works out, and the x minus 2 is a part of it. There are days where I'd rather write one of the bigger numbers first before x minus 2, but that's totally fine. That means negative 1/3 was a factor and negative 1/2 was a factor. There were going to be no other whole numbers. They were going to be these ones right here, negative 1/3, negative 1/2. I probably would have had to test it at some point. Maybe there is one that we run into that does have all of those. I don't know. We'll see. All right. Number 7. Now, I'm looking at number 7, and two things come to mind really fast. Number 1 is a factor. Well, your only chances are 1 and negative 1. I didn't think about that. But number 2, I think I could factor this by grouping. And I'm going to use synthetic division. I mean, they tell us, wait, what do they ask us to do? Find the rational zeros of the polynomial function in the right and factored form. I find one of them, and then I factor the rest out. But I think you could factor this one by grouping looking at this thing. This is x squared times x minus 1 minus 1 times x minus 1, which is then x squared minus 1 times x minus 1, if you know the factoring by grouping, the video below. X squared minus 1 factors to x minus 1, and then there's x plus 1, and then times x minus 1. So this factors to x minus 1 quantity squared times x plus 1. So this should be the final answer here, or these are the factors we should get. And that totally makes sense. The factors of p over q are just plus or minus 1, right? P over q is plus or minus 1. If I test, let's plug in 1. 1 minus 1 is 0. Minus 1 plus 1 is 0. So f of 1 works. Now, you wouldn't do all these steps here if you already knew that factoring by grouping worked. I thought the goal of these was they weren't going to give ones that were factorable by grouping, therefore, blah, blah, blah. But this is a good way to show that this is the same answer we're going to get anyway. So I I do synthetic division on 1 here with 1, negative 1, negative 1, and 1. And we'll get 1, 1, 0, 0, negative 1, negative 1, 0. So this becomes x squared minus 1 as that factorization. Golly gee, I never expected that. With x minus 1 being the factored guy right there, and then it leads you to the rest of it. That leads you then to this, and leads you then to this. Excuse me. So that's the answer through synthetic division, testing that one out. Seems like one of the smaller, getting easier ones to do there. And that works. This one doesn't seem to factor by grouping. If you're wondering if I know how factoring by grouping works, I'm seeing my pairs and know the common factor that fits within pretty easily, proportionally. Specifically with these numbers all being 1s, it wasn't actually that much of a challenge. You can't factor by grouping here, though. And when I say you can't factor by grouping, what I'm also kind of inferring is that there is no binomial times binomial setup of it ever. Even if one of the binomials factors down more, these were never binomials times binomials. It was a binomial times a trinomial. And then 3 binomials multiplied. But again, binomial times trinomial here, binomial times trinomial here. All of those were those. This is a binomial times binomial. That's what factoring by grouping will give you. These other ones don't do that from the onset. It'll be some binomial times trinomial, and I'll use synthetic division to work it. So my p's and q's on this one, I got it. It's factors of 12 over 1. So plus or minus 1, 2, 3, 4, 6, and 12. I'm excited to get a 12 one of these days, maybe. I don't know. 1 minus 1, 1's not going to work. Negative 1. I don't think negative 1 works. I'm gonna go to the calculator with this one here. I'm gonna do my official first one on this guy. So let's do x cubed. I just wish I could type in calculators faster. Plus x squared. The variable is harder to find here. I never use this one for this. Minus 8x minus 12. So I plugged in my equation here. You probably can't see it in full. That's okay. I'm just going to try numbers. Just take my word for it. Ooh, I didn't type enter correctly to edit the function. X cubed. See, I'm having trouble. Plus, I should have been plugging things in. X squared minus 8x minus 12. All right. I'm going to try some numbers here. Let's try 1, 2, 3. I'll let you know if I find a 0. 3 is a 0. All right. So f of 3. See, if you type in the equation and ask for things, it'll go fast. F of 3 is 0. Where are my roots? Let's find out by doing synthetic division on the rest of this. 1, 1, negative 8, negative 12. All right, here we go. Synthetically divide. Okay. So that becomes x squared plus 4x plus 4. That's a perfect squared trinomial as far as I know. So x minus 3 times x squared plus 4x plus 4. Two numbers that multiply to 4 and add to 4 are 2 and 2. This is, this is x plus 2 quantity squared, like that. That's what this guy factors down to. I guess that's what they wanted 7 and 8 for, to show you that you get, one of those, one of those. Looks pretty good. All right, I still have 4 more of these kinds of problems to do, and then I have a word problem down there. So numbers 9, 10, 11, 12. Now we have a 5-term polynomial, quartic, right here, and we're still testing things. It's still with q's over p, or p's over q's, I should say. So the same test as before, same numbers, 1, 2, 3, 4, 6, and 12. Let's try 1. 1 plus 5, because 1 might work. 1 plus 5 is 6, minus 1 is 5, minus 17 is negative 12, plus 12 is 0. 1 does work, and that's good. Now, the thing is, we might have to factor more than once. If the cubic does not factor by grouping, then we're going to have to find another rational root here, because factoring quadratics is quite easy when factorable as far as finding what's there. Factoring cubics, even if factorable, you might have to use rational root theorem again, right? I guess that's what makes these problems a little bit longer here. So f of 1 being 0 means let's go ahead and test this out, because I don't know if the cubic's factorable by grouping or not. I have no idea. 1, 5, negative 1, negative 17, and 12 right there. So let's check it out. 1, 1, 6, 6, 5, 5, negative 12, negative 12, and 0. Okay, so this, because that's not factorable by grouping. So this factors into, right now, guys, as it stands, this factors into x minus 1 times x cubed plus 6x squared plus 5x minus 12. Now we need to take this and factor it down more. And like I said, it's not factorable by grouping. It's not. So what we have to do is find another rational 0. Now, I want to let you know, and I'm looking at it right now, and it's true. Remember when I said that these are possible rational zeros? They can occur more than once. We just saw it twice. We just saw it back here. There's 2 instances of x equals 1 here. It's a multiplicity of 2, and this has only 1 instance of negative 1 right there. There's 1 instance of 3 right here, and there are 2 instances of negative 2 right there. So, don't skip 1 this time. As I look at this thing, if I'm testing this polynomial expression, and I'm trying to do f of 1, f of 2, for these things here, look at 1. 1 cubed is 1, plus 6, plus 5 is 12, minus 12 is 0. There's another 1 factor. So I'm going to, once again, use synthetic division, but use it on these guys right here. Let's do it one more time here. I didn't know that was the case, but it's going to be. Let's do it on 1, 6, 5, and negative 12, and see what we come up with there. That's 1, 7, and 12, with 0 remainder. And we get that x squared plus 7x plus 12. So this factors into x minus 1 times x minus 1. I'll put them together later. Times x squared plus 7x plus 12. We've seen this before. That factors into x plus 3 times x plus 4. So in total, this factors to x minus 1 quantity squared times x plus 3 times x plus 4. Which means negative 3 and negative 4 were your other 2 roots for this thing. But 1 occurs twice. And I tested both times, and it worked both times. So, test 1 on your own. I think it's a pretty fast test to do. And look, they gave us more space to do these. I think they assume this is going to happen. All right, this one right here, x to the 4th minus 6x cubed plus 11x squared minus 6x. There's a common factor of x. I'm going to go ahead and factor that one out to start, right? Common factor of x. I get now a cubic, x cubed minus 6x squared plus 11x minus 6. And, that is important because your factors of q are factors of your constant term. There's only one. No, I take that back. But factors of your constant term, the only things I'd test are factors of 0 divided by whatever. I'd first just test 0 out from it. And then once 0 works, because 0 is a factor, right? X equals 0. By the way, I don't know if they said find the rational zeros. I'm writing out the factors and I'm telling you these are the rational zeros. I don't write it each time. I find one rational 0, then I divide. But 0 is one of them. X equals 0 is one of your zeros. But I'm not worried about that anymore. Now I need to factor this one down right here, which still cannot factor by grouping or anything. So I'm going to now test factors of 6 divided by factors of 1. So my p's over q's this time are plus or minus 1, 2, 3, and 6. Let's, of course, test 1 here. 1 minus 6 is negative 5 plus 11 Negative 5 is 6. Minus 6 is 0. So 1 works again. I'm always happy when it does, even if testing is more important for you guys to learn through some of these. Kind of saves me time. So f of 1 is 0. Let's test 1 as a root right here. We'll have 1, negative 6, 11, negative 6 there. So 1, 1, negative 5, 6, 6, and 0. All right, so this factors down to, what was the first one? X, boom. X minus 1, boom, and then x squared minus 5x plus 6, which factors into x minus 2 times x minus 3. So this factors x times x minus 1. Hey, check this out. X minus 2 and x minus 3. That's kind of cool. Who knew that this would become this thing up here? I did not. So your zeros, by the way, are x equals 0, 1, 2, and 3. Those are your zeros. Cool. All right, 2 more before the word problem here. X to the fourth minus 2x cubed minus 3x squared plus 4x plus 4. Once again, not factoring by grouping with 5 terms. With this, was this one 5 terms? No, that one was. I'm not going to factor by grouping with 5 terms here. I don't even know really where to start with that. But this thing goes up 1, 2, 3, 4. Oh, 4 and 4. I guess they needed to make sure that it was factorable. Maybe a 5 there wouldn't have worked. Anyway, factors of 4 divided by factors of 1. So my p's over q's this time are plus or minus 1, 2, and 4. Hopefully it's making sense what I'm doing there. I'm dividing these by plus or minus 1 right here, and they're only positive, only integers from it there. Let's try 1. 1 minus 2 is negative 1. Minus 3 is negative 4. Plus 4, nope. Let's try 2. So we'll get 16 minus, I think that's also 16, which is 0, minus 12 plus 8 plus 4. I think this one works. So 0, yes, that one works. So f of 2 works there. So let's go and synthetically divide. A lot of little rough work there. 1, negative 2, negative 3, 4, and 4. Let's check it out. 2, 0, 0, negative 3, negative 6, negative 2, negative 4, and 0. Okay, so from here, this becomes x cubed minus x, minus 3x minus 2. So x minus 2 is one of your factors. And then x cubed minus 3x minus 2. One of which, be careful, you are not in, I don't think something can factor anyway, but this is not a quadratic. You're not finding what two numbers multiply to make negative 2 and add to make negative 3. This is a cubic still. And being a cubic, that means that unless you can factor by grouping, I should use rational root theorem again on one of these to check this thing out. Now, I'm not going to try 1 again. I mentioned I should try ones again that, worked, whatever. I'm not going to try 1 again. If 1 didn't work here, it's not going to work here. Right? 1 minus 3 minus 2, whatever, it's not going to work. 2 could still potentially work. It's a possibility. In fact, we're not even testing 4 anymore. 4's out. We're testing factors of plus or minus 2, plus or minus 1. Right? I have a new p over q set to refer to because I've diminished my values. Plus or minus 1, plus or minus 2. 1 doesn't work. That's out. Negative 1's possible. But 1 doesn't work. Let's try 2 again. 2 cubed is 8. Minus 6 minus 2. It works again. That's another f of 2 right there. Right? 2 is another 0. Another f of 2 is 0. So now we know that this factors... Oh, I have to divide. So divide 2 one more time with 1, 0, negative 3, and negative 2. Remember 0 being a placeholder for x squared. So that's 1 times 2 is 2 plus 0. 2, 4, 1, and 2, 0. So this becomes x squared plus 2x plus 1, which is actually a perfect square trinomial there. So this is x minus 2 times x minus 2 times x squared plus 2x plus 1. X squared plus 2x plus 1 is x plus 1 quantity squared. So this is x minus 2 quantity squared times x plus 1 quantity squared. They're sure having fun with all the different answer types that we can actually see there. Ooh, getting close to 45 minutes here. And this last one, this is factorable. Let me give you the factorization first. This is x squared minus 4 times x squared minus 1. If you've worked with some of my u substitution things, working that out, that's what this would be, which becomes x plus 2 times x minus 2 times x plus 1 times x minus 1. So this is what the final factorization would be. I mean, I didn't use rational root theorem. They're not requiring that we do. If you want me to do it one more time, I can. I'm going to test 1 as a thing, and it's going to work here. So my p's over q's are plus or minus 1, 2, and 4. As I test 1, 1 minus 5 is negative 4, plus 4 is 0. So f of 1 equals 0 works. Let's work that 1 and divide it out. That's a 1x to the 4th plus 0x cubed minus 5x squared plus 0x plus 4. Synthetically divide there. And we get this. We get x cubed plus x squared minus 4x minus 4. Now, I'm kind of going to cheat myself here in a second because I was just stating, this factors into that times x minus 1. Because I just stated I don't want to do this by factoring, I wanted to use rational root theorem. Well, this one I can factor by grouping. I mean, at what point do I stop using rational root theorem to test? I'm going to stop right now. I'm going to factor by grouping here, show you another factoring by grouping thing. X squared factors out here and I get x plus 1. Negative 4 factors out of here, I get x plus 1. And so this thing, and remember there's an x minus 1 right there, right? So then that factors into x squared minus 4 times x plus 1 times x minus 1. And x squared minus 4 is x minus 2 times x plus 2, all that. So we get the same answer there, regardless of which way we look at it, right? All that pans out. Your roots are 2, negative 2, 1, and negative 1. Plus or minus 2, plus or minus 1. Anything that wasn't the 4, plus or minus 4 there, worked out. Okay, one more here. Manufacturing. A laboratory supply company is designing a new rectangular box in which to ship glass pipes. The company has created a box with a width 2 inches shorter than its length and a height 9 inches. I didn't know this is what the wrong was. 9 inches taller than twice its length. The volume of each box must be 45 cubic inches. What are the dimensions? So let's say a rectangular box. So think of like a prism here. We're gonna have a rectangular prism. Volume is represented by length times width times height. So if I have, width here, length here, and height here, something like that. Looks like we can express everything in terms of what? What'd they say? Length? So if the length is L, the width is 2 inches shorter than the length, L minus 2. The height is 9 inches taller than twice its length, twice the length and 9 inches taller. And of course, L is L. So if volume is length times width times height, and if I substitute, for volume, I'm going to substitute 45. And if I substitute, here's L times here's W, and here's, what does that have to do with? Oh, I know why. Here we substitute H, 2L plus 9, that equals 45. I was going to say, what does this have to do with rational root theorem and such? Well, this isn't set equal to 0, so you can't use zero product property right here. What we have to do is we have to distribute this guy. I'm actually going to FOIL these out, work that. And then I'm going to multiply it by L. Let's see if I can do this all in my head. It should get 2L cubed plus 5L squared minus 18L, I believe. And I'm going to subtract the 40, not equals. I'm going to subtract the 45 over here because I need to set this equal to 0 to work these things out the way I'm trying to. We want to find answers to length based on this thing here. What value of L will give us 0? We don't have to write it as a polynomial this time. This time we just want to solve straight up. I can factor this by grouping. Should I use synthetic division? I'm going to use synthetic division one more time. This whole thing's on rational root theorem in my book. I'm going to go ahead and use it. If you know how to factor by grouping, you know what? I always got to show factor by grouping for those who want to look at it and say, I'm not going to use rational root theorem if you can factor by grouping here. Common factors afoot right here. You can factor out an L squared and you're left with 2L plus 5. Here, if you factor out a negative 9, you have 2L plus 5. And that equals 0. You know what? I'm gonna stick with this. We've done synthetic division quite enough. I'll say this. If you test your P's over Q's, your factors of 45 go up here. I'm not going to do it, but I'm just showing you the things that you can use. Oh, sorry, 5. I skipped 5. Plus or minus 5, 9, 15, and 45. And then your factors of Q go down here, 1 and 2. It's possible you're looking at factors that aren't just plus or minus 1, 3, 5, 9, 15, 45, but plus or minus 1 half, 3 halves, 5 halves, 9 halves, 15 halves, and 45 halves. Those are the possible ones to test. Hopefully a nice small one works. In fact, I know 1 or 2 that will work here. Anyway, factoring by grouping, that's L squared minus 9 here with 2L plus 5 here. Listen, all this stuff equals 0. We're trying to solve, but we can keep factoring here. L plus 3 times L minus 3 times 2L plus 5 equals 0. So L either equals negative 3, positive 3, or if you do 2L plus 5 equals 0, subtract 5, divide by 2, you get negative 5 halves. So those are the 3 different possible answers for L, but we're not done with this whole thing, because what do they want? There are a couple things I still need to say. Do they want dimensions? What are the dimensions? We need the length, the width, and the height. I found length, sort of. And then we find width and height, obviously based on length. That'll be pretty straightforward. But length is a physical property. Length needs to be positive. There are 2 solutions here that don't work. Negative 3 is not positive. Negative 5 halves is not positive. The only positive one is 3 here. It's the only one that applies. Yes, these values can substitute into here and they give me a W and an H, but those might be then negative as well. And then it gives me a 45 when you multiply all 3 numbers, but they're not positive numbers. 3 is the only one that does work for that. Let's work off that to get the rest. And hopefully the width and height should be the same. W is the length minus 2, which is 1. And the height is 2 times the length plus 9, which is 6 plus 9, which is 15. So, are these inches? What were these? Inches. So, your dimensions are 3 inches in length by 1 inch in width by 15 inches in height. I actually did not use synthetic division that time. Factoring by grouping allowed me to, but P's over Q's, you would have either found 3 or negative 3 as your factors there if you want to check it out. And negative 5 halves would have been one of them. Check that out. Negative 5 over 2 would have been one of them there as well. Okay, so I know I did a lot of jibber jabber there, 50 minutes in. The rational root theorem explained it to begin with, but I rushed pretty much at the end there. Hopefully you know synthetic division and some of the other things. If not, it could have been a lost art for you guys. That'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. The next one, you're going to see a lot more of this, but with complex numbers. You're going to want to know quadratic formula or possibly completing the square when we look at complex I values, and synthetic division is still going to be something to know. All right, guys, thank you so much for watching. Take care. I will see you in the next one.